Hello, welcome to the presentation Big Data in Healthcare Systems. In this presentation, we will introduce the concept of big data and why it is important in the field of healthcare systems. In addition, we will make a walkthrough of the most popular big data techniques available today. The author of the presentation is Javier Esparza, and this is a virtual avatar, automatically generated for guiding you throughout this presentation contents. In the next slides, we will briefly discuss about the role of big data in healthcare. Then we will present a reference architecture of most big data systems. After that, we will explore the two main approaches available in big data processing: batch processing and stream processing. All right, let's discuss why big data is necessary. Today, there are many sources of information which generate datasets so large and complex that they are difficult or impossible to manage with traditional techniques. For example, elderly people may use wearable devices for monitoring their health condition, sending measures about blood pressure, heart rate, glucose level, body temperature, etc. Another example involves mobile phones used today by almost everybody, which contain sensors like the GPS, accelerometer, gyroscope, etc. Just another example are the social networks, where lots of messages about sentiments or reactions to multiple events may be collected. All these sources of information generate so much data that using traditional stores, tools, and techniques is not feasible. By leveraging big data technologies, it is possible to discover associations and understand patterns and trends in the data. Big data analytics has the potential to improve care, save lives, and incur lower costs. For example, a recommendation system in healthcare may provide clinical decision support for professionals. These systems may analyze data aggregated from multiple patients and suggest the most plausible diagnostic or recommend the most cost-effective treatment. Another example is an epidemic surveillance system. By analyzing data from search engines and social networks, the system is able to detect in very early stages an epidemic disease breakout, faster indeed than other official channels, such as the World Health Organization. All data acquired by wearables are very useful for monitoring individuals' health condition. In addition, by analyzing these measures, it is possible to proactively identify individuals who would benefit from preventative care or lifestyle changes. Thus, big data technologies take advantage of the huge amount of data to extract insights for making better informed decisions. All these improvements allow optimizing the available resources. Medical facilities may be relieved, saving costs related to hospitalization, and enhancing healthcare services by improving waiting time for consultations. But what is big data? How can we decide whether a particular source of data is big data? Big data refers to large digital datasets that combine the following characteristics, commonly known as the 3 V's. Volume means high amounts of data. Velocity means data gets generated at a rapid pace. Variety, it means data comes from many different sources and under different formats. The 3 main V's have been further extended to many more V's recently, which add more features to the datasets. For example, value refers to extracting additional value from the data. Veracity refers to the quality of data produced. Variability refers to changes in data rate, format, structure, and semantics, etc. But how does a big data system look like? Most big data systems adopt a well-known reference architecture. We present a particular variant of such architecture in this slide. As you can see, the architecture strongly resembles the path followed by the data. The following global components can be identified: data sources, data collection, data cleaning, data analysis and interface, and visualization. The data sources component includes all the sources of data. Data collection refers to the tools and processes required to obtain data from data sources. Data cleaning refers to the tools and processes required to clean, validate, filter, and integrate data. Data analysis includes the tools and processes to obtain higher-level information, which will be helpful for more intelligent decision-making. Finally, interface and visualization refers to the tools used for displaying the results in a graphical and intuitive way. In addition, it is very common to export interfaces for making data available to external systems. In the next slides, we will describe with further details each of these components. The data sources component includes all the sources of information of the system. Regarding the structure of the provided data, it is common to classify data sources as either structured, unstructured, or semi-structured. Structured data sources supply data conforming to a strict data model. These data are easy to process. An example would be relational databases, whose data must verify a given schema. Unstructured data sources provide data with no structure, which makes them more difficult to process. Some examples are media data like pictures or music, or free text included in regular files or web page content. This type of data is by far the most common at any organization, around 80% of the total according to Gartner. Finally, semi-structured data sources have some internal structure but are not strictly typed. These data typically have a flexible schema, which is easy to evolve. Some examples are XML and JSON documents. Data sources can also be classified regarding data mobility. Following this category, they can be either in situ or stream data sources. In situ data sources keep data at a particular location and must be consulted periodically. This is the case of centralized databases. Stream data sources generate continuous data streams which must be consumed in real time, like for example social media feeds. In the context of healthcare, we can find a great deal of relevant data sources. For example, electronic healthcare records, EHRs, stores are in situ data sources which contain complete patient medical history in digital format, including patient status, demographics, medications, diagnosis, laboratory tests, doctor's notes, radiology documents, etc. All these data may be given in a structured or semi-structured way. Another example are biomedical images, which represent an in situ unstructured data source very valuable for disease detection. Social networks and search engines represent a stream semi-structured source of information very interesting for discovering infectious illnesses. For example, one can obtain information about people's reactions and monitor the conditions of epidemic diseases. Sensing data obtained from different wearables or from the mobile phone's integrated sensors represent another stream semi-structured source of very valuable information for determining the health condition of patients and predicting future diseases. Data collection includes all the processes required to obtain the data from the external sources. If the data source is in situ, the system executes extract transform load processes, periodically executed by batch processes. They may take a long time until data is available. If the data sources are streams, then data are typically obtained through fast delivery to the system's message queues, enabling real-time processing of the received data. Due to the vast amount of data to transfer, especially for in situ sources, it is very common to compress data before transferring them. Regarding data cleaning, it includes all the processes used to transform the raw data into valuable information easy to consume by the rest of the system's components. It is common to consider the following subtasks. To check the received data are valid, according to some predefined rules. To filter data, removing all noise included in the data. Detect and remove repeated data. Transform data to a form easy to consume. To store data in intermediate stores. In any case, the result of this phase are data ready to be consumed by subsequent phases. Data analysis refers to all tasks and processes executed to obtain further insights of the data. In general, the healthcare domain has 4 categories of analytics: descriptive, diagnostic, predictive, and prescriptive analytics. The goal of descriptive analytics is to describe the current situation. The tools typically used include statistical techniques and data aggregation operations, like histograms and charts. An example would be obtaining the number of patients admitted. Regarding diagnostic analytics, they explain why certain events occurred and their causes. Some useful tools are clustering and decision trees. An example would be trying to understand the reasons behind the regular readmission of some patients. Predictive analytics has the ability to predict future events. To that end, it identifies patterns and trends in data, and it is able to determine the probabilities of future events. To that end, it is very common to use machine learning techniques. An example would be to predict whether a patient can get complications with a particular treatment. Finally, prescriptive analytics is able to propose actions leading to optimal decision-making. To that end, multiple possibilities are explored, typically by using simulation techniques, and the results are evaluated. Then the most optimal decision is recommended. An example would be recommending not to give a particular treatment to a patient in the case of a harmful side effect with high probability. The last step in this brief review of a big data systems architecture is the component named Interface and Visualization. In this component, the data analyzed must be presented to the user in an intuitive and meaningful way. It may take different forms. A useful tool is a dashboard, where all data gets summarized and the user can get an idea about the current status and detect existing trends. More sophisticated techniques may be used though, like augmented or virtual reality. To conclude with, the obtained data are usually published to third-party tools through automated interfaces. It is common to classify big data techniques around two generic groups: batch techniques and streaming techniques. Batch techniques have been with us for a long time. Thanks to advances in hardware and communications, streaming techniques are gaining popularity recently. In the next slides, we give more details about these two general techniques. First, we begin discussing batch processing. The term batch comes from the days of punched cards, when programs were executed one after another in batch mode. Today, batch processing means a job reads large volumes of data, processes them, and generates some output. This processing does not require user interaction, it is executed offline instead, and usually takes a lot of time to complete. This is the reason why these jobs are usually scheduled to run at particular points in time or periodically. MapReduce is a widely adopted algorithm in the field of batch computing. It was invented by Google for processing very big files. In particular, Google first used it for creating indexes for their search engine. The algorithm consists of two main phases, which are executed sequentially: the map phase and the reduce phase. In the map phase, big files are broken into multiple blocks, and each block is processed by a mapper in parallel. The mapper is a function which receives the data included in a block, and then extracts the required data, filters, and transforms them in such a way that is useful for the next phase. In this phase, lots of data get generated. It is considered an expansion phase. In the reduce phase, all the data generated by the mappers gets sorted and forwarded to multiple reducers. A reducer is a function which receives the data generated by the mappers and accumulates or summarizes or aggregates them in order to obtain the desired outcomes. Even though it looks rather specific, this algorithm has proven to be useful for solving multiple problems. Its main strength lies in its scalability. It is able to process very large files in very big data centers. The more machines a data center has, the faster the results will be obtained. Multiple experiments have been reported working successfully in data centers with thousands of machines. In addition, MapReduce implementations must be fault-tolerant. This means when a node fails, the system must detect the failure and restart all the lost jobs in a healthy node. The second group of big data techniques is known under the term of stream processing. In this case, data are generated in a continuous way, called stream. Data are acquired in an asynchronous way and receive the name of events. Many data sources may be modeled as a stream of events. For example, considering user graphical interfaces, user interaction may be modeled as a stream of events, like the click of a button, the selection of a list, etc. If we consider IoT devices, all the measurements obtained by their sensors can be modeled as a stream of data. Even data stores can be considered a stream of data if we just focus on the updates they receive throughout their life cycle. The main strength of stream processing techniques is they are able to process data as they are received in almost real time. To that end, an intermediate element called message queue is required, also known as messaging system or message broker. This element is able to ingest thousands of messages per second and to route them to the appropriate destinations. In such a system, a publisher publishes events, typically under a given topic. Then a consumer subscribes to the same topic. The message queue is responsible for receiving the events from the publisher and routing them to all registered consumers. Stream processing is characterized by processing events using architectures pipe and filter, which means different filters may be applied to every event in sequential order, in different phases. In this way, multiple filters can be connected by pipes, configuring complex stream processing networks. Thank you for your attention.